So on review, homework review. Oh goodness, why are you green? Homework review 2.6b, related rates. It was page 157, and I had you doing numbers 16 through 21 all, and then 26 and 29. So a little bit more complex related rate type of questions. Maybe some formulas that you're not sure how to create. We can go over some of these. I may not do the whole problem of every one, but like I may get it set up for you so you can then finish it. But which of these questions would you like me to go over? Which of these would you like me to start on? It was page 157, 16 to 21 all, 26 and 29. You want all of them except 16. And I'm sure someone else out there would like number 16, huh? So I guess we'll just go through some of these. What I'm going to do then, I'll go through as many as I can and set up the equations for you and then let you solve the rest. So let's start with a few of these. Now recall the steps here. Basically the steps for solving any related rate question are: 1, find the equation. Maybe slip 16. Got it, Barry. So sure thing. Step is find the equation, ddt it, do the derivative, plug in your known numbers. Sometimes you have to solve for an unknown. Sometimes you have to do a little bit of manipulation to find the missing piece. And then find, or solve, I guess, find the answer. I don't know. Solve it. So 17. 17 asks us to find a sand and gravel plants. Sand is falling off a conveyor onto a conical pile. So helpful drawing, right? Conical pile of sand. Conical pile of sand. Little conveyor belt. Conical pile of sand. At a rate of 10 cubic feet per minute. So there is our dV dt. Change in volume over change in time. Cubic feet per minute, right? Sand falling onto this conical pile at 10 cubic feet per minute. So maybe even step 0 would be to draw it out. Really a helpful way to start this is drawing it out. The diameter of the base is approximately 3 times the altitude. Okay, so diameter of the base, diameter is 3 times the altitude of the pile, which they don't tell us either one, but we know this relationship. We know that the diameter is 3 times the altitude. So, at what rate is the height of the pile changing? So we want, let me do, not A, let me do H here. Let me do, this is H, because that's height. So they want to know, what is dH dt equals question mark, dH dt. At what rate is the height of the pile changing when the pile is 15 feet high, when H is 15? They don't tell us anything about the diameter or the rate of the diameter changing, anything at all. But they do tell us the diameter is about 3 times the height. And that relationship is going to be very important. This relationship here is going to become very important because all we're given is the height. So, formula, we know the volume of a cone, 1/3 pi r squared h. One-third pi r squared h. So I know this equation. Do I do a derivative immediately? Well, I'm going to say not yet. Because the problem here is I have an r, and I don't know any information about r. I don't know what dr dt is, I don't know what r equals, but I have this relationship with the height. So a common sort of situation, sometimes you will have to replace, or substitute one variable for another. Another. For example, r here, well, if I know the diameter is 3 times the height, that means that the radius is 3h over 2. And I can take this 3h over 2 and plug that in for the radius here. And now the only variable I have is the height. This is a very common, tricky thing. Pi, and then I've got 3h over 2, h squared. Now the only variable I have is height. And I can rearrange. I can do a little bit of 1/3 pi 9h squared over 4 times h, which I'm going to just rearrange all of this a little bit. 9 and 3 will cancel out, so I'm going to get 3 pi h cubed over 4, and that's the volume. Right, because h times h squared times h. So that is the kind of situation sometimes you end up with where you have to plug in one variable for, substitute a variable for another, so that you can replace one and you have an equation now is only a single variable. And now if we did ddt, you could find that answer. Because you're looking for dh dt, you have h is 15, you have the change in volume. Where'd that go? You have the change in volume was 10 cubic feet per minute. 10 cubic feet per minute. You have dv dt, you have h, and that's all you need to solve for dh dt. All right. So this kind of trick here, this was the key part here, our little trick of replacing the radius with h, doing a substitution. And they have a few questions that are like that. Where they relate one variable to another. So again, I said that I would show you the equations and let you finish the rest of this problem. So that's for number 17, everybody. The rest, try that on your own. Do that derivative, solve that problem. Let's look at 18. Same situation, right? Same situation, number 18. We have now a volume of oil in a cylindrical container. So we have a cylinder. And it says the volume is increasing at a rate of 150 cubic inches per second. The height is, it says, approximately 10 times the radius. 10 times the radius. Okay. At what rate is the height of the oil changing when the oil is 35 inches high? So we want to know dH dt. We want to know dH dt. We don't know what R is, but we know that the height at the moment, the height of the oil at the moment, when it's 35 inches, is H. So we have these relationships. Again, they have this connection here. Right? The height is 10 times the radius. Or we can rearrange that and say the radius is equal to the height divided by 10, right? Doesn't matter which way we put it. One of these is going to be more useful than the other. Which direction do we do the substitution? That's our question here. So let's get our formula. Volume of a cylinder is pi r squared h. Volume of a cylinder, pi r squared h. We know that this is dV dt, change in volume. And I know I want to find dH dt. I want to find dH dt. So in my equation, I want to have dH dt. I don't really care about dr dt. In fact, dr dt is probably going to be 0, right? It's a cylinder, the radius isn't really growing. But I have this radius here, I have this height here. Do I want to plug the h in for r, or do I want to plug the r in for h? Which one do we want to have? Do we want to have h or do we want to have r? That's our question now. Do we want h only or do we want r only? And it depends. The answer is depends what we want. Do we want h only or do we want r only? And it depends what the question is asking for. What is this question asking for? What do we want to find in this problem? Someone in the chat tell me, what do we want to find? What is it asking us to look for? Yeah, it's wanting to know dH dt. It says, at what rate is the height of the pile, at what rate is the height of the oil changing when the oil is 35 inches high? At what rate is the height changing? So we want to know dH dt. So the only variable we want to have in this situation is h. That's the one we want to keep. And we want to get rid of the r. So I'm going to use this r equals h divided by 10 and do that substitution in here. I'm going to put this r in for r in for r here. Now I'm going to do this, make a little note here so you know to do this in the future. Since we want dH dt, we only want h in the equation. Since we only want dH dt, we want only h in the equation, so I'm going to replace the r in terms of h. V equals pi h over 10 squared h, which is pi h cubed over 100. and then we do ddt of that, and we get our situation, get our equation. Does that make sense? Right, we want dh dt, so we only want h in our formula. And that's how we determine how to manipulate these variables around, manipulate this formula around when we have one variable in terms of another. So you get your equation, get your derivative, plug in those other things, and solve for the missing piece, which I'm going to let you do on your own. 19. Burning through these, everyone. 19, we have this swimming pool. We have a swimming pool. It gives us some information. This is 3. This is 1. This is 6. The width is 12. And the change in volume, it says, is one quarter of a cubic meter per minute. And that's our dV dt. It also tells us that there is currently 1 meter of water in the pool at the deep end right now. One meter of water in the pool at the deep end right now. Great. What percent of the pool is filled? What percent is filled? How do we do this? I don't like that. What percent of the pool is filled with 1 meter of water at the deep end? How do we figure this out, everybody? What can we do to get volume? So really, I need to find out what percent is filled. I need to find some formula for the volume of this pool. This is some strange shape. This pool is some weird shape. How do I find the volume of this shape of this pool? Now let's think back to our geometry days. How can we figure out the geometry of this situation? What is the formulas for volume? Maybe you didn't get to that in your geometry class, but we got to figure it out. We got to figure out volume. We got to figure out how do we determine the different parts of this pool here. Got some water in here. It's going up to there. 1 meter tall here. 1 meter tall here, filled with water. How do we fill it? How do we figure out the volume of this? If you do not remember about the volume of complex shapes like this complex shape is called a prism. This complex shape is called a prism. A prism because it has one side that is the same on both sides. These two, like, not exactly triangles, but these are trapezoids on both sides, right? You got a base here, and some height. These are two trapezoids on the side here and on the side here. And you have a trapezoid that's like spread across this distance of 6 meters. 6 meters here. So I'll measure meters. Meters, 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 meters. So when you have a shape like this kind of shape is called a prism. And to find the volume of a prism, is always the base area times the length or height, you could call it the length of the prism. This is the general formula for any kind of prism shape, and it's true for lots of shapes. For example, a cylinder. So how do you spell cylinder? Cylinder. A cylinder is a kind of prism. You have a base and a base, two circles, and a height, right? Try to draw a better circle here. A cylinder is a kind of prism. You get the idea, close enough. Our base in this case, the base of the prism is going to be this circle here. And this circle here. So what's the area of a base of a circle? What's the area of a circle? Area of a circle. We have a circle spot, right? Area of a circle is pi r squared. Area of a circle. The length of the prism in this case is the distance that we stretch it up and down. Right? So we have this circle, and you can imagine it kind of like stretching across this space, extruding across some length, some distance. So we have this base circle stretching across a space. An area times a length. Area times length gives us volume. Gives us a three-dimensional volume. So pi r squared times this thing here, we call it the height. And that's the formula for the volume of a cylinder. Pi r squared h. And that's why it's the formula, because you have a circle times the area of a circle times the length that the circle is being stretched across. The area of a circle times the length of the space the circle is stretched across. Pi r squared h. So this is true of every type of prism. Every type of prism, this is really bad. Prism. Every type of prism has this same formula. And no matter how complex it is, right? If it's a triangular prism, you have, well, like this, in this case, we have a hexagonal prism. No, this is a, what do I call them? Trapezoidal prism. Right? The base here, in our prism here, this is a trapezoid. Trapezoid. So I got to figure out what is the area of a trapezoid. The area of a trapezoid. Okay, now I got to remember that formula. 1/2. Anybody remember? 1/2 of something times something. There's a plus in here. What was the area of a trapezoid? Oof. It's almost like a triangle, but it had some other things happening. Area of a trapezoid. Anybody remember? Type it in the chat if you got it. 1/2 of something plus something times something. Area of a trapezoid. Trapezoid? Well, I've got just very similar to a triangle. Very similar to a triangle. Area of a triangle is 1/2 base times height. Problem with the trapezoid is we have two bases. We have this base over here, 3, and this other base over, right, this base over here of 3, and another base over here of 1. And so to like compensate, the area of a trapezoid is 1/2 of base 1 plus base 2 times the height. And that is the area of a trapezoid. So that's the area of this little side of the pool. Base 1 is 3, base 2 is 1. Height is going to be this here. This is h. Call this base 1, call this base 2. Height, because it's the 90-degree right angle from one base to the next. That's what the 90 degrees is. It's not this. This is not the height, right? Because this is diagonal. This flat 12 meters is the height because it's the height from one base to another, right? Maybe if you rotated this trapezoid, you'd see it better, right? Maybe that's better. 3, 1, and 12. So that's your trapezoid area right there. So that's the area of the trapezoid. What is the length of the trapezoid of the prism? So we take this area here, the area of this shape, and we stretch it this way. Stretch it across the pool, and that's 6 meters. That is the length, going to be this one right here that we stretch it. So, taking all of that, volume of this trapezoid, volume is going to be 1/2 of base 1 plus base 2 times the height of 12 times the length of 6. And that's going to be our volume of this trapezoid, of the whole thing. Okay? So this is going to be, let's see, 2 plus 1 is 4, half of 4 is 2, 2 times 6 is 12, 12 times 12 is 144 cubic meters is the volume of this pool. Volume of the whole pool. Great. But what did it want from us? What did it want from us? It didn't want us the volume of the pool. What did it want? What are we trying to figure out? We got the volume of the whole pool. Well, what do I need to do next? What part's missing here? What's my information? What do I need to know? We're trying to find out what percent of the pool is filled. I know if the whole thing is filled, it's 144 cubic meters. I want to know what percentage is filled with water right now. So I need to know how much water is there. How much water is there? That's what I need to know. I've got the volume of the whole pool. Well, now what's the volume of water? How much water is this? It's 1 meter deep. I know it's 6 meters across. What's the volume here? How big is this? How much water is that? How could we figure out the volume of this water in this pool? 1 meter deep. I know this is 6 meters across. How do I find the volume of that? Volume of this water. Yeah, exactly, Perry. So exactly. Perfect. This water is a little triangle, right? Got a little triangle here. Little triangle. And it's got an area just like a prism. This is the area of the triangle times the 6 meters across gives me the volume of water in the pool. There you go. So, what is the area of the triangle? So let's do this volume of water. The volume is 1/2 base times height times 6 meters across. Base area of the triangle times the length of that triangle. Okay, well, I've got 1/2 of. Base is 1. Height. Height. This length right here is unknown to me. I don't know the length of this. How do I know how long this is going to be? How could I possibly figure out the length from this spot of the water till wherever it is over here? Nope. This is where a lot of people might say, take the book, throw it out the window, go play some video games, right? This is where we got so far, and now still one thing we don't know. How can we do this? How can we do this? But no, we will persist. We will figure it out. You know why? Do you know why, everyone? AP Calculus. That's where we are. That's where we are. We can do this. And I'm going to show you a trick to figure out how to do this. Another geometry trick that if you don't remember your geometry, yeah, that's a good guess, Perry. So good guess. SOHCAHTOA, right? We could maybe use some trigonometry. Maybe we can figure out, like, imagine, like, let me do this in yellow. Imagine this triangle here cutting from the bottom. Oh, God, that's really bad. Cutting from the bottom across. No. bottom, oh goodness, bottom across the shape to the other side, but then the height's not 3. I don't know. So maybe not. Well, then I guess maybe the height wouldn't be 3. Then it would be 2, wouldn't it? Because if this is 1, we have a little triangle here of 2. So we got a little mini triangle here of height 2, and a little minier triangle of height 1. Little mini triangle of height 2. And a little minier triangle. So maybe if I use, and this is still 12, so maybe I could do SOHCAHTOA, find the angle here, and that's the same angle as the triangle here, and then I could do SOHCAHTOA again to figure out this. That's a way you could do it. Yeah. We'd have to use, what, like tangent, I think, TOA, opposite adjacent, inverse tangent, find the angle, and then do the tangent to that angle to find the missing side. Sure. There's a better way. There's a better way. AP Calculus manual, like I said. To find, let me do this. Let me do it in green. I haven't done green yet. To find the H for the water, we can use triangle ratios, proportions. Right, we can use proportions. I've got my little blue triangle here. My little blue triangle is, we're going to do this. My little blue triangle, I've got height of 1 and length of h. And then I got my yellow triangle. I've got a height of 2 and a length of 12. And I know these two triangles are proportional. I know these two triangles are proportional. They have to be matching because they are the same pool. It's the same pool. So if that side's 1, that side's 2, if that side's 12, yeah, proportions come back to bite you. If I know the relationship between these triangles, they're all the same triangle, 1 to 2, 12 to what? What is the h going to be? Look at the proportions, everyone. What's the h going to be? Matching the sizes, it's just a stretched out different triangle. What size is my h? Very good. My height's going to be 6. My proportion here is 1 to 2, right? This is half as big. This side is half as big as this side, 2 to 1. So this side is going to be twice as big as this side, 12 to 6. Half as big. Half as big, half as big. So my area, my area of the triangle, I know my height is 6. I can use that to find the volume of the triangle. 1/2 of 1 times 6 times 6. 6 and 6 is 36. Half of 36 is 18 cubic meters. So the proportion that is filled, the volume of water is 18 cubic meters. The volume of the pool is 144 cubic meters. So the proportion is percent filled is 18 divided by 144. Which, let's do a calculator here. 18 divided by 144 is about 12.5%. 12.5% filled. Whew. Wasn't that fun? I thought that was fun. This is how teachers enjoy themselves. Find the volume of this pool. Find the volume of the water using trigonometry. Well, not really trigonometry. Geometry, ratios, proportions. I used the yellow triangle, right? Because I made my little triangle. I got down by 1, dropped the height by 1. So instead of 3, now it was 2. So I had my 2 and 12 and 1 and 6 triangles, proportional. Got all that stuff together. And you learned about how to find volumes of prisms. Take the base area times the length it's stretched across. Works for any kind of prism, triangular prisms, trapezoidal prisms, any kind of prisms. Found the volume, found the water, found the percent filled. Okay. Part B. I wanted to go through this because these questions are very important, like knowing how to do all this process with the geometry, with the proportions, with like the tricks of the trade. This is the tricks of the math. These kinds of things are the tricks of the math trade, figuring out, looking at problems and breaking it into pieces that you can solve with some tools that you have, like this volume formula, like this proportion idea, right? All these kinds of ideas. Part B asks, at what rate is the level of the water increasing? We're pouring in some water at 1/4 cubic meter per second, or per minute. At what level is the water going up? So now we have to do a little bit of calculus. Part B. What level is the water increasing? So I want to know, let's call it dh dt. Right, again, I've got my prism here. Got my water. Water is 1 right now. I want to know what is the height of the water. How is the height of the water changing? I know when it's 1. I know this is 6. I know the volume of the water. I know how much water there is in the pool, right? Got that information, right? So the volume of water is, because all I care about is the volume of water. It's 1/2 base times height times 6. This length of 6 isn't changing. Now length of 6 isn't changing. I guess I got to call these different things here, right? Instead of base, let's figure out our nomenclature here. This, let's call, instead of dh, let's call this b. Call this b, since that's our base, really. That's our base. We use that as our base. So let's call this the change of base. I mean, it doesn't really matter, but we know the idea. Base, height, we know those. So how much is this 1 increasing with the volume change from there? So I got 2 variables that are changing. This 6 is not going to change. This 6 is stationary. But base and height, those 2 things are going to grow, right? As the base is going to grow. So how do I relate these things to each other? I could use that same proportion, but 2 over 12. And how I found the height here. I found the height, right? We found this height here. We said 1 over h equaled 2 over 12. That's what we said before, right? So h, I guess, is going to be, well, but it's, instead of 1, this is going to be b. So let's say h is equal to 12b over 2. I think this is what we have to do to find h. I thought we had till 11:40. Am I wrong? Oh man, I'm way off. Sorry, everybody. Just getting too into it. All right, we'll pick this up again tomorrow. Try this out. We got a few of these. Sorry, everyone. Let's just keep on going. We'll, like I said, we'll pick this up again tomorrow. In the chat, type goodbye. Once you type goodbye, you're free to go. Sorry, everybody. Thanks for sticking around.